Okay, thank you. So I was asked to talk here, and really encryption plays a very little role within the L1 roadmap. There's two places where it comes up. One is secret leader election. So it's this idea that you don't want to know publicly who the next leader is, and this is good, for example, to protect against denial of service attacks. And then the other place where it comes in is encrypted mempools, which is basically the subject of today's talk. And interestingly, both of these types of encryption are ephemeral, right? They only last a few seconds or a few milliseconds even, as we'll see here. Now, I've been spending a lot of time on preconfs, and they're basically a way to change the paradigm for block building and mempools and user confirmations. Okay, so we basically had this evolution of the desiderata of mempools. First, we wanted to do something very simple, which we wanted to prevent front-running. Right? If you publish your transaction on a public mempool, you will get sandwiched, for example, if you are interacting on Uniswap. And so we just wanted to do something very simple, which is to protect front-running. And then there's the fancier version of encrypted mempools, where you could do computation on the encrypted transactions themselves, and you can imagine, for example, OFAs, where searchers kind of compete to give you the best backrunning, if you will, like the best execution. And for that, you need to go from simple encryption to like homomorphic encryption. And now we have this new requirement that I'm adding to the mix, which is that we want real-time user experience. So we want the user to not only get best execution, no front-running, and like good back-running, but we also want them to know within a few milliseconds that that transaction will be executed on-chain, and this is how the transaction will execute. Okay, so the talk will be in two parts. I'll try and give you a flavor of what preconfs are. This is maybe like the newest material for you guys, and then I'll kind of talk a little bit about how the existing ideas on encrypted mempools need to be adjusted a little bit for preconfs. So let's introduce a little bit of terminology. Right now we have the notion of a slot, which is a unit of time, for example, 12 seconds in the context of Ethereum. And what we're going to do is we're going to zoom into the slot, and we're going to break it down into a new unit, which we call the ticks. So I'm actually stealing the nomenclature from Solana. Solana has 12.5 millisecond ticks. It has 32 ticks every slot, and every slot is 400 milliseconds. So yeah, there's also Mega ETH that has this new notion of a 1 millisecond tick as well. It's basically a more granular way of dealing with time. And then another piece of nomenclature that I want to put forward is the notion of a shred. And again, I'm stealing this term from Solana. So you have a block, and if you zoom in, oops, something's wrong with the slide here. Basically, you should imagine the block being kind of cut into pieces going from top to bottom, and basically each slice being a shred. Okay, so what is a preconfirmation? A preconfirmation, what is the basic idea? As a user, I know who the next sequencer will be because it's in the look ahead. So the emoji here, 1, 2, 3, 4, stands for sequencer. It's because it's ordering transactions 1, 2, 3, 4. And the user basically needs to identify the sequencer and send them their transaction and say, please, sequencer, can you execute my transaction in advance before you even build the block? And the sequencer says, sure, I promise to put your transaction in position 10, and your Uniswap price will be $12 per token. And the way that these preconfirmations are made credible is through collateral. So the preconfer, the sequencer, has some collateral. And if a promise was made, but the preconfirmation was reneged, meaning that what happened on-chain did not match the promise that was made before the block was built, then there's some slashing. And there's two types of faults. There's so-called safety faults and liveness faults. So safety faults is when I promised to include your transaction in position 10, and then I included just a completely different transaction on position 10. And the liveness fault is I promised to include you in position 10, but actually my block didn't make it on chain. It was a missed slot. I got reorged out. Okay. So sorry about the slides. Maybe the conversion to PowerPoint broke them. But basically, we have this new notion of real-time building. Here, on the right-hand side, we can see that the block is partially built. That's the blue portion. And the user brings their transaction, the orange transaction, and is basically asking the sequencer to just append, from top to bottom, the transaction. So it's a different form of building, which is more, instead of being monolithic, it's kind of real time. And then the promise comes back from the sequencer. But one important detail here is that in some sense there's no mempool, like it's a direct connection from the user to the sequencer. The sequencer itself is maintaining the mempool, and it's very low latency, right? Because the latency is going to be 1 ping time, so the amount of time it takes for the user to reach the sequencer, plus 1 tick time, which is the internal amount of time it takes to process the shred. But the kind of little detail that I want to present, because it's going to be relevant later on, is that actually the user, instead of sending a transaction per se, it's going to send something more abstract, which is an intent. So for example, I want to buy a token and I want to get best execution. This is a more abstract thing than a specific transaction. And this intent is going to be sent to a searcher. The searcher is going to return kind of this best shred. So there's going to be a competition between the searchers, and then the best result will be returned to the sequencer, and that's what the sequencer will put at the top of the block after what's already been built, and then it's going to return that promise of the best shred to the user. Okay, now let's go into the encryption part, unless there are questions about preconfs. Any questions? I guess we take 1 or 2 questions about preconfs.
As I understood the terminology, shreds are about time. How can you talk about the best shred? How can we intuitively understand that?
So the term for time is a tick. The term for space is a shred. So a shred, you can think of it as kind of like a bundle or a transaction. Yeah. And the second question.
Sorry. So I'm also not super deep in the Solana stuff like you were talking about, but I think there's like a notion of like continuity there, like continuous block building, versus like a lot of the pushback on pre-confirmations has been like tampering in an auction by like delaying the execution for a block and basically extracting more value that way. So I was wondering like how that kind of fits in. I think the encrypted mempools would be like an interesting way to like help with that. But anyways.
Right, so there's 2 aspects here. Like one is like the structure of building, and there's this notion of real-time building where you kind of build the top from top to bottom, shred by shred, tick by tick. And like structurally speaking, this is the same thing as Solana today. And then you may ask, okay, what are the incentives? Like what's the game theory? Like how will this play out? And you make a good observation that there's this incentive, for example, to take the request and kind of hold it and basically only include it at the very end of the slot. And this is something that we don't see on Solana right now because Solana is somewhat unsophisticated in its block building. But if someone were to have a modified client of Solana that does these clever strategies, then it would be earning more MEV, and I expect that to happen in a matter of months. Like these strategies will happen on Solana, and we need to think of them also in the context of pre-confirmations. Okay, great questions. Part 2, the encryption. So really what we want is this notion of a credibly fair auction, right? Like the sequencer is the auctioneer, and it's having to deal with users and with the searchers. And as I mentioned, there's 2 aspects of best execution. There's the no front running and the best back running. So in order to prevent front running, what we do is we just have the transaction be encrypted, like from the user sending it all the way to the auctioneer, so that there's like no man in the middle. And ideally, we want to be in a position where even the auctioneer doesn't see the contents of the transactions, because the auctioneer could be malicious and kind of insert its own front-running transactions. And then there's another aspect of the credibly fair auction, which we want the best backrunning. And in order to get the best backrunning, we need very high competition, right? We need the searchers to feel very comfortable participating in this auction. And in some sense, what we want is we want to have encrypted searcher strategies, right? So this is something that SUAF and Flashbots are doing, right? They have this platform where they invite searchers and solvers to put forward their strategies, but those are encrypted and executing within TEs. And because it's this neutral kind of encrypted platform that doesn't leak alpha, right? Like if I'm a very sophisticated searcher, for example, I'm Jared from Subway, or I'm Beaverbuild, or whatever it is, I can like privately run my strategies and not leak them. So this is another important aspect of where encryption comes in. Now, really the hard part of encryption is actually not the encryption itself, right? Really, encryption is easy. Like you have this pub key, you encrypt against the pub key, that's easy. But the hard part is the decryption. And there's kind of two things that we want. One is decryption minimalism. We only want to decrypt what is strictly necessary. And then the other hard part is we want to decrypt at the exact right time. If we decrypt too early, it's bad. It allows for front running. If we decrypt too late, it's bad for user experience. And so this is where the decryption minimalism comes in. So we want to take all the state of your system, so that includes the user intent and transactions, as well as the searcher strategies, as well as the feeds. So feeds could be, for example, like data prices on Binance and whatnot. So the searchers would feed like encrypted data in real time. You want to have all of this be encrypted, and then you want to do your process of committing to this encrypted data. You want to do execution, like all the homomorphic stuff. And then you want to decrypt, and this is where the minimalism comes in. You only want to decrypt what has to go on-chain. Well, the shreds have to go on-chain. Like they're literally like public data that goes on-chain. So can we only have the shreds be decrypted? And the answer, I guess, is yes. And what we want to do is we want to do these 3 steps here: the commit, execute, and decrypt in one single tick, in something like 10 milliseconds. So we're really talking about very ephemeral encryption. And the first step here, the encryption, basically is one ping time. It's like from the user all the way in flight to the auctioneer. And yeah, as I mentioned, we want to make sure that the timeliness is just right. Now, there's various flavors of encryption that have been like considered as candidates for encrypted mempools. And one of the basic things that we want is this notion of guaranteed output delivery. So we want to make sure that if something gets encrypted by a user, there's some other process that doesn't involve the user to decrypt the transaction. So like one example is, well, let's just go through all the flavors. So the simplest flavor is just centralized encryption. You just trust an entity, like MetaMask, that is now, since a few weeks ago, running its own encrypted mempool. And you have the first logo, which is MEV blocker. So the idea of MEV blocker and MetaMask is that I send my transaction to a centralized entity, end-to-end encrypted, and this centralized entity will promise to not leak my user transaction and include them in blocks without anyone being able to front run. And in some sense, you can think of it as being like legal encryption. Like there's legal contracts between the encrypted mempool auctioneer, and the searchers that they work with. Now, the next kind of flavor of encryption is enclave encryption, TEs. And this is what Suave is working on. And then there's the threshold encryption. And I guess we're missing the Fhenix logo. Sorry about that. But I know that Arbitrum is working on an encrypted mempool, which is threshold-based. There's Shutter, and there's various other projects. And then another very interesting way to get this kind of guaranteed output delivery is with delay-based encryption. So you encrypt a message, and then if someone does sequential computation over a period of time, for example, 5 minutes or like 5 milliseconds, then it just magically decrypts itself. And then the final like crazy, most sophisticated version of encryption where you have this notion of guaranteed output delivery is witness encryption. So you encrypt your plain text under some abstract witness, and anyone who can provide the witness can decrypt the plain text. So for example, the witness could be the Ethereum chain has finalized, right? You can have a finality certificate. You provide that as a witness to an encrypted ciphertext, and then that will allow you to compute the plain text. Okay, now it turns out that, let's see, witness encryption is just a moon math that is not ready today, so let's just discard it for now. And then the delay encryption is actually kind of awkward, and the reason is that it involves adding artificial latency in various places, and that goes against the real-time aspect of pre-confirmation. So really we're left with these 3 different flavors of encryption that we can work with. And my specific kind of strategy for builders that want to build this is to take the fake it till you make it approach, which is to start centralized, which is what we have today. We have things, as I mentioned, like MEV blocker. We have things like the MetaMask. We also have a Flashbot Protect. So there's basically this fracturing of many different encrypted mempools, each privately run and centrally run. And actually, one of my predictions is that within the next 12 months, the public mempool will be dead. There will be maybe 10% of the transactions that go in Ethereum blocks that will go through the public mempool. Everything else will go through these encrypted mempools. And there's 2 big reasons. Like, one is that users get better execution because they don't get front run. But like there's another reason, which is the wallets are incentivized to do this because right now they're capturing the back run. So instead of users capturing the benefits of the back run, it's the wallets themselves, and they're making a lot of money, millions of dollars per month, to extract this from their users. And then, the next easiest thing, I guess, is enclave encryption. And there's this excitement around TEs recently, and I share this excitement, and I hope someone builds encrypted pre-confirmations in the TEs. But then, the end game, I guess, is threshold-based. I still have 1.5 minutes for questions. That's the end of my slides. Thank you. Any questions? I'm happy to pass the mic, and I have a microphone here as well.
So could we imagine that we cancel an intent in a tick? So imagine that at tick T1, we are not happy with the state of the chain because we didn't know the previous transactions. Is there a way that we could just, cancel?
So I guess you're asking, is it feasible to solve intents within 10 milliseconds? Is that the question? And do you know the state of the chain at that point?
No. So you said that with the so in every slot you're gonna split in different ticks, in 32 ticks.
Yes.
But as a user, I don't know when my transaction is gonna be. included in,
Right, correct.
because I don't know the previous transaction, the previous transaction that the previous ticks.
Yeah.
So imagine that my transaction was based on some assumption.
Right. Okay. Yeah. Okay. Great question. So, from the perspective of the user, like, if you really want to know the state of the chain after every tick, you can do that, because the expectation is that every time a shred is pre-confirmed, it's made public. And so, if you really want to care about the state of the chain, you can do that. But if you have some sort of assumption about the pre-state root, you can encode that in your intent. You could say, only execute my intent if, for example, I get at least $12 per token on Uniswap, or the pre-state matches these conditions. So this is something that you can encode in the intent. And so, yeah, it is possible that the intent can't be fulfilled, in which case, the answer that you get is, sorry, we can't fulfill your intent. But if the intent is fulfillable, then you have this guarantee that you get the best possible outcome, because you have the searchers competing against each other to fill your fillable intent. Okay, thank you.
Great job.